Hey everyone! Today we're diving into one of the universe's most fascinating and mysterious phenomena, black holes. Now, I know what you might be thinking: black holes sound complicated, maybe even scary. But I promise you, by the end of this video, you'll understand exactly what they are, how they form, and why they're actually one of the coolest things in our universe. Black holes have captured human imagination for over a century. They've been the villains in sci-fi movies, the subject of countless documentaries, and in 2019, we even captured the first ever photograph of one. But what exactly are they? Let's break it down in the simplest way possible. Number. What exactly is a black hole? 2 to 5. At its most basic level, a black hole is a region in space where gravity is so incredibly strong that nothing, not even light, can escape from it. And I mean nothing. Not particles, not radiation, not even information, according to some theories. Think about it this way. When you throw a ball up in the air, Earth's gravity pulls it back down, right? Now imagine if Earth's gravity was so strong that when you threw that ball up, it could never come back down because it would need to travel faster than the speed of light to escape. That's essentially what's happening at a black hole, except the gravity is millions or even billions of times stronger. The reason we call them black holes is pretty straightforward. Since light can't escape from them, they don't emit any light. They're literally black. We can't see them directly, which makes them incredibly challenging to study. But just because we can't see them doesn't mean we can't detect them. We'll get to that in a bit. Now, here's the really mind-bending part. Black holes aren't just empty voids in space. They contain an enormous amount of mass packed into an incredibly tiny space. To understand this better, let's talk about density. Imagine taking all the mass of our sun and crushing it down into a sphere just 6 kilometers across. That's the kind of extreme density we're talking about with black holes. Number. The anatomy of a black hole. 5 to 8. Every black hole has two key features that define it: the singularity and the event horizon. The singularity is the very center of the black hole. This is where all the mass is concentrated into what physicists call an infinitely small point. Now, when scientists say infinitely small, they really mean that our current understanding of physics breaks down at this point. The singularity is where the laws of physics as we know them stop making sense. It's where gravity becomes infinite and space and time become infinitely curved. Then there's the event horizon. This is probably the most important concept to understand about black holes. The event horizon is the boundary around a black hole, the point of no return. Once anything crosses this invisible boundary, it's gone forever. The event horizon isn't a physical surface like the ground beneath your feet. It's more like an invisible sphere surrounding the singularity. Think of the event horizon as the ultimate one-way door. You can go in, but you can absolutely never come out. The size of the event horizon depends on the mass of the black hole. The more massive the black hole, the larger its event horizon. For a black hole with the mass of our sun, the event horizon would be about 3 kilometers in radius. For a supermassive black hole like the one at the center of our Milky Way galaxy, which has a mass of about 4 million times our sun, the event horizon is about 12 million kilometers in radius. That's roughly the distance from the sun to Mercury. There's also something called the photon sphere, which sits just outside the event horizon. This is a region where light can actually orbit the black hole. Imagine light traveling in circles around the black hole, trapped by its gravity but not quite pulled in. It's a bizarre concept, but it's real. Number. How black holes form. 8-11. So how do these cosmic monsters come into existence? There are actually several ways black holes can form, and they come in different sizes depending on how they're created. The most common type is called a stellar black hole, and these form when massive stars die. Here's how it works. Stars spend their lives in a constant battle between two forces. Gravity is trying to crush the star inward, while the nuclear fusion happening in the star's core creates an outward pressure that pushes back. As long as the star has fuel to burn, these forces stay balanced. But when a truly massive star, we're talking at least 20 to 25 times the mass of our sun, runs out of fuel, that outward pressure disappears. Suddenly, there's nothing to resist gravity. and the star's core collapses in on itself in a fraction of a second. A supernova. During this supernova, the outer layers of the star are blown away into space, creating beautiful nebulas that we can see with telescopes. But the core? The core continues to collapse. If there's enough mass, more than about 3 times the mass of our Sun, the core collapses all the way down into a black hole. The gravity becomes so strong that not even the fundamental forces between particles can stop it. Then we have supermassive black holes. These giants can have masses ranging from hundreds of thousands to billions of times the mass of our Sun. Almost every large galaxy, including our own Milky Way, has a supermassive black hole at its center. Scientists are still figuring out exactly how these form, but the leading theory is that they grew over billions of years by consuming gas, dust, stars, and even merging with other black holes. There are also intermediate mass black holes, which fall somewhere between stellar and supermassive black holes, and there's even a theoretical type called primordial black holes that might have formed in the very early universe, just moments after the Big Bang. These remain hypothetical for now, but scientists are actively searching for evidence of them. Number, time, space, and black holes. 1114. Now we're going to get into some really wild territory. Black holes don't just bend space, they bend time itself. This is where Einstein's theory of general relativity comes into play. According to Einstein, massive objects actually warp the fabric of space and time around them. Imagine placing a bowling ball on a trampoline. The bowling ball creates a dip in the trampoline's surface, right? That dip is similar to how massive objects curve space. Black holes create such an extreme curve that it becomes a bottomless pit. But here's where it gets really strange. Time itself runs differently near a black hole. The closer you get to a black hole, the slower time passes for you relative to someone far away from it. This effect is called gravitational time dilation. Let's do a thought experiment. Imagine you have a twin, and you decide to fly your spaceship close to the event horizon of a black hole while your twin stays on Earth. From your perspective in the spaceship, everything seems normal. You check your watch, and time seems to be passing normally. But if you could somehow look back at Earth, you would see everything moving incredibly fast, like watching a movie on fast forward. Meanwhile, your twin back on Earth is watching you through a telescope. From their perspective, you appear to be moving in extreme slow motion. Your every movement takes hours, then days, then years from their point of view. If you got close enough to the event horizon, your twin would watch you appear to freeze almost completely, never quite crossing that boundary. And if you did cross the event horizon, from your twin's perspective, you would appear to freeze at that moment forever, your image becoming redder and dimmer until it fades away completely. But from your perspective, you'd cross it in finite time and continue falling toward the singularity. This isn't science fiction, this is what Einstein's equations tell us actually happens. Black holes are literally time machines in a sense, though not the kind you can use to visit the past or return from. There's another fascinating aspect to this time dilation. It means that black holes are, in a way, windows to the future. If you could somehow survive orbiting very close to a black hole's event horizon for what feels like a few hours to you, and then return to Earth, you might find that thousands, or even millions of years, have passed on Earth. Your brief journey would have carried you into Earth's distant future. This concept was brilliantly portrayed in the movie Interstellar, where the crew visits a planet orbiting close to a massive black hole. They spend just a few hours on the planet's surface, but when they return to their ship, they discover that more than 20 years have passed for their colleague who stayed behind. While Hollywood took some creative liberties, the basic physics shown there is actually accurate. The warping of space-time near black holes creates other strange phenomena too. Light itself gets bent around black holes, creating what's called gravitational lensing. If you were to observe a black hole with stars behind it, you wouldn't see a simple dark circle blocking those stars. Instead, you'd see the light from those background stars bent and distorted around the black hole, creating multiple images, rings, and arcs of light. It's like the ultimate cosmic funhouse mirror. Einstein's equations also predict something even more bizarre: rotating black holes. When a black hole spins, and most do, Because the stars they formed, horizon is so far from the singularity that tidal forces at the event horizon are much weaker. You could theoretically cross the event horizon of a supermassive black hole without immediately being torn apart. But don't get too excited, you'd still be doomed once you got closer to the singularity. The reason for this difference lies in the size of the black hole. Remember how I mentioned that more massive black holes have larger event horizons? Well, the gradient of gravity, how quickly it changes over distance, is less steep for larger black holes. So while a stellar mass black hole might rip you apart from thousands of kilometers away, a supermassive black hole's event horizon could be millions of kilometers from the singularity, giving you a much gentler approach, at least initially. Once you cross the event horizon, there's no turning back. All paths lead inward. In fact, the singularity isn't even a place you travel to. It becomes a moment in your future that you cannot avoid, like tomorrow. No matter which direction you point your spaceship, you'll end up at the singularity. Space and time swap roles inside a black hole in a way that's difficult for our minds to comprehend. Think about it this way. Right now, you can move freely through space in any direction you choose. Forward, backward, left, right, up, or down. But you cannot move through time in any direction. You can only move forward into the future. You can't go backward to yesterday or sideways to an alternate timeline. Inside a black hole's event horizon, this relationship flips. The direction toward the singularity becomes like time. You must move in that direction, just as you must move forward in time. There's no going back, no stopping, no changing course. The singularity is in your future as inevitably as tomorrow. The entire experience from crossing the event horizon to hitting the singularity could take just fractions of a second for a stellar black hole, or potentially hours for a supermassive one, depending on the black hole's size. During that time, you'd see some truly bizarre things. The universe behind you would appear compressed into a shrinking circle, becoming brighter and more blue-shifted as you fall. Meanwhile, any light that fell in before you would be visible, meaning you might see a historical record of everything that ever fell into the black hole, all compressed into the final moments of your journey. But here's one of the strangest paradoxes in all of physics: the information paradox. According to quantum mechanics, information cannot be destroyed. Every particle, every bit of data about the state of something, must be preserved in some form. But black holes seem to violate this rule. When something falls into a black hole and hits the singularity, what happens to all the information about that object? Does it get destroyed? If so, that would violate one of the fundamental principles of quantum mechanics. Stephen Hawking spent much of his career working on this problem. In the 1970 seconds, he discovered something remarkable. Black holes aren't completely black after all. They actually emit a faint glow of radiation, now called Hawking radiation. This happens because of quantum effects right at the event horizon. According to quantum mechanics, empty space isn't really empty. It's filled with pairs of virtual particles that pop into existence and annihilate each other almost instantly. But at the event horizon of a black hole, something interesting can happen. One particle from a virtual pair can fall into the black hole while the other escapes. To an outside observer, it looks like the black hole is emitting radiation. Over incredibly long timescales, we're talking trillions upon trillions upon trillions of years, this radiation would cause a black hole to slowly evaporate, eventually disappearing completely. This creates an even deeper version of the information paradox. If a black hole evaporates completely through Hawking radiation, what happens to all the information about everything that ever fell into it? Does it get encoded in the radiation somehow? Is it truly lost? Physicists are still debating this question, and it's one of the biggest unsolved problems in theoretical physics. The answer might require a complete theory of quantum gravity, a theory that successfully combines quantum mechanics and general relativity, which we don't yet have. Number. Black holes and the fate of the universe. 1922. Let's zoom out and think about black holes on cosmic scales. Black holes aren't just interesting objects to study. They play crucial roles in the evolution of galaxies and potentially in the ultimate fate of the universe itself. Almost every large galaxy has a supermassive black hole at its center. and these black holes appear to have a profound influence on their host galaxies. Studying black holes also helps us understand the universe's history and evolution. Black holes are cosmic time capsules in a way. The supermassive black holes at the centers of distant galaxies show us what conditions were like billions of years ago. By studying how black holes have grown and evolved over cosmic time, we learn about how galaxies formed, how stars lived and died, and how the universe transformed from the hot, dense state after the Big Bang to the vast, structured cosmos we see today. Black holes also teach us humility. They remind us that the universe operates according to laws that can seem bizarre and counterintuitive to our everyday experience. Time slowing down, space being curved, information potentially being holographically encoded. These concepts challenge our assumptions about reality. They remind us that the universe is stranger and more wonderful than we might imagine. And there's something profound about humanity's ability to understand these objects at all. Black holes represent some of the most extreme and alien environments imaginable. Yet, through mathematics, observation, and careful reasoning, we've been able to figure out how they work. We've gone from Einstein's equations written on paper in 1915 to photographing the shadow of a black hole 55 million light-years away in 2019. That's an extraordinary achievement of human intellect and cooperation. Common misconceptions about black holes. 26-0, 28-0. Before we wrap up, let me address some common misconceptions about black holes, because there's a lot of misinformation out there. Misconception Hasson. Black holes are cosmic vacuum cleaners that suck everything in. This is probably the most common misconception. Black holes don't suck any more than any other massive object. If you replaced our sun with a black hole of the same mass, which you can't actually do, but let's imagine Earth would continue orbiting exactly as it does now. The gravitational pull at Earth's distance would be identical. Black holes are only dangerous if you get very close to them, within a few times the radius of their event horizon. The difference between a black hole and a regular star of the same mass is that you can get much closer to a black hole before hitting a surface. With a normal star, you'd hit the star's surface long before gravity got strong enough to trap you. With a black hole, there's no surface to stop you, so you can fall all the way to the event horizon where gravity becomes inescapable. Misconception #2. Black holes are holes or tunnels to other places. Despite the name, black holes aren't holes at all. They're not tunnels to other universes or wormholes to distant parts of space. They're extremely dense objects with mass concentrated at the singularity. The name black hole is really just a description of how they appear, or rather, don't appear to us. A more accurate name might be dark star or frozen star, but black hole stuck because it's more evocative. Now, some theoretical solutions to Einstein's equations do suggest that certain types of rotating or charged black holes might contain passages to other regions of spacetime. These are called Einstein-Rosen bridges or wormholes. But these solutions are purely mathematical and likely don't exist in nature. Even if they did, they'd be incredibly unstable and would collapse before anything could travel through them. Misconception #3. Nothing can escape from a black hole. This is mostly true, but with an important caveat. Nothing can escape from inside the event horizon. However, things can and do escape from near a black hole outside the event horizon. In fact, some of the most powerful phenomena in the universe involve material escaping from the vicinity of black holes. When material falls toward a black hole and forms an accretion disk, not all of it necessarily falls in. Some can be ejected in powerful jets that shoot out perpendicular to the accretion disk at nearly the speed of light. These jets can extend for thousands or even millions of light-years into space. They're powered by the intense magnetic fields and rotation near the black hole. And remember Hawking radiation? Over extremely long timescales, black holes actually do emit radiation and gradually evaporate. So, in a sense, information and energy can eventually escape from a black hole, just in a very different form and over incomprehensibly long periods. Misconception #4. Black holes are rare. Actually, black holes are surprisingly common. As I mentioned earlier, there are likely hundreds of millions of stellar mass black holes in our galaxy alone. Every galaxy, with more than a few billion stars, probably has a supermassive black hole at its center. When you consider that there are hundreds of billions of galaxies in the observable universe, the total number of black holes is staggering. The reason they seem rare is simply that they're incredibly difficult to detect unless they're actively feeding or have a companion.